Okay, thank you. I would like to thank the organizers for inviting me, and also for the very having to count all the details in the organization, to be very kind. Um, and well, today I will talk about the fermionic dark matter halos from a maximum entropy principle. I am from CONICET and La Plata National University, and also in collaboration with ICRANET, Italy. And the works I will present here are a series of recent papers published in the last years, and the works has been done in collaboration with these people here, half of them from Italy, and the last 3 people from Argentina, La Plata National University, and the last 2, my PhD students, Santiago Collazo here in the audience. Okay, let me start with, there is a bit mismatch here. Okay, let me start with the dark matter halo formation mechanism from collisionless relaxation. So as you know, the basic equation for dark matter halo formation for collisionless particles is the so-called Blasov-Poisson equation, which is no other than the Boltzmann equation, in which the right-hand side you have a 0 for the collision terms. This F is the fine-grained phase space density, which generally depends on time, and it is coupled with Poisson through this equation here. So as you know, this is the standard equation from n-body simulation with 3 codes, where anything, but maybe I touched something now. So as you know, this is the standard equation for n-body codes, but I will show in this talk an alternative way of dealing with the dark matter halo formation in terms of kinetic theory approaches and thermodynamics. It is possible, it has been shown already that by making an expansion of the decomposition, sorry, of the phase space density into a coarse-grained phase space density, F bar, plus fine-grained fluctuations, and you replace this to the Blasov equation, it is possible to lead to another equation in which the right-hand side resembles the Blasov equation, but in the right-hand side, you put all the fine-grained fluctuations averaged, and this is so-called a diffusion convection equation in which you have this diffusion current. So the challenge here is to solve or to find most likely phase space density at relaxation from this equation. Of course, this is a very difficult task, but it has been worked out by Pierre-Henri Chavagny in the 1998 from a maximum entropy production principle. So by asking that the diffusion current is a constant, it is possible to find the most likely coarse-grained phase space density at relaxation from this equation by asking that the system maximize the entropy production towards the relaxation, right? So interestingly, you find a phase space density solution of Fermi-Dirac type, as you can recognize in the denominator. And in the numerator, you have a term which tells you that for energies of the particles above an escape energy, you have your system evaporates particles, and there you have your system stops there, right? So this is very interesting because probably you know the Lynden-Bell theory of violent relaxation. So Chavagny was able to generalize and formalize the original theory of Lynden-Bell in this kinetic theory approach, and including for evaporation of particles. So now the challenge of this talk will be, if we want to work with fermions in the fermions as the building blocks of the particles, we will have the maximum phase space density occupation number, eta 0, which proportional to the particle mass to the 4th divided by the H Planck cube. So this is the statistics for fermions. So therefore now let's try to build dark matter halos from this, out of this coarse-grained phase space density. The first key concept here is that fermions under self-gravity do admit a perfect fluid approximation. This was demonstrated by Rufino and Bonassola in the 1969 by solving the Einstein-Dirac equation. So if this is the case, therefore we can try to solve the Einstein equation for a gas of fermions at finite temperature and hydrostatic equilibrium, so working with the Tolman-Oppenheimer-Volkoff equation in spherical symmetry. We have done this starting from the this coarse-grained phase-space density of Fermi-Dirac type, as I shown in the former slide, then to build an equation of state out of this coarse-grained phase-space density here as the integrals of this phase-space density, and implying a 4 free parameter theory, which is the particle mass, a dimensionless beta temperature parameter called beta, the degeneracy parameter, which is chemical potential over kappa T called theta, and the cutoff energy. Then we proceed to write the coupled system, highly nonlinear coupled system of ordinary differential equations, which is the mass equation, the Tolman-Oppenheimer-Volkoff equation, the Klein, Tolman, and energy conservation. These are written in this dimensionless manner. And as you probably know, the Klein and Tolman are the zero and first law of thermodynamics in general relativity, which is coupled to the Tolman equation here. And therefore, this is implies a boundary condition problem to be solved, which we will work out for regular solution at the center, not singular. So the mass is not singular, and the free parameters of the theory will be less free, and therefore we wonder ourselves which is the most general solution for this system of equations. Okay, interestingly enough, the most general solution provides a novel core halo, which has interesting applications to dark matter profiles in galaxies. And these profiles from outer to inner parts, when you solve this boundary condition problem I told before, when you solve for realistic typical spiral halo values, for example, 10 to 4 parsec at the 1 halo scale length here and to the mass of 10 to 11 solar masses, then you solve for these fixed halo boundary conditions, and you find out that the outer part resembles a pseudo-thermal sphere, which is similar to a Nastor core than Nastor or NFW halo tail, but towards the center, due to the fact that we are considering the Pauli principle in the equation of states, you have this very dense and degenerate core of fermions, in which this core is supported by degeneracy pressure, while continuously linked in a continuous manner this quantum regime to the classical regime, while the halo is supported against gravity by thermal pressure, right? So this is an interesting solution because you have the two regimes in one system covering a very different order of magnitude in radius, from milliparsec to 10 to the 2 parsec, or 10 to the 5 parsec. One important point of this equation is that it can be demonstrated that for central degeneracy larger than 10, typically, the dense core fulfills the so-called quantum condition. That is that the thermal de Broglie wavelength is always larger than the interparticle mean distance. So that's why you can call this like a quantum core. And these dark matter profiles depend on the particle mass, which is a very interesting feature of these models, in contrast with standard profiles in the literature. Then one may wonder, okay, you have this nice halo behavior, which resembles the traditional profiles in the literature, but what about this core? What about, is there any realization in nature of this new signature? So we'll try to answer this question in this challenging way, which is, can the overall gravitational potential explain, if we want to apply to the Milky Way, right? Explain the Milky Way rotation curve, but also the S-star dynamics, and without the central black hole hypothesis? Meaning, we will try to provide an alternative picture to the central black hole to be instead of in terms of dark matter. So in order to solve this problem or answer this question, we will work with this boundary condition problem. We will ask for the core of dark matter to be the mass of the central object in Sagittarius A star, so 4 million solar masses, and two different constraints for the mass at typical halo scales, the later one from Gibbons and Bell-Kurob of Sagittarius dwarf satellite. So Well, the answer is yes, interestingly, and there is not only one solution to answer for this question, but there is a family of solutions of this core halo nature, in which in this picture of the left, I show a family of density profiles in which solutions from the black curve to the dashed gray, they go from particle masses from 48 keV up to 345 keV, and all of these solutions for fixed halo boundary conditions, the central core is dense enough or compact enough in order to answer for in this plot of the right, for the average circular velocity of the 8 best resolved S stars around Sagittarius A star. And interestingly, when baryons dominate in the bulge and these regions, the dark matter profile in the rotation curve has a minimum when the bulge peaks. So do not spoil the baryonic contribution that we know that has to be in this intermediate scale, and then rises towards the boundary of the galaxy, in which we know we need the dark matter content in order to explain the nearly flat behavior of the rotation curve. I also comment about that Santiago Collazo, my PhD student, did a very nice work performing a very nice galaxy rotation curve fitting with the state-of-the-art machine learning tools with the steepest gradient descent method, improving these fittings. Because here we have only fixed 3 boundary conditions, and the solution also already provide a good fit. But it can be improved this with a better fit. And let me just mention one more important point, is that why this particle mass range? This is because for lower particle masses than 48, because there is a relation that the larger the particle mass, the more compact the quantum core. Therefore, and vice versa, right? Therefore, for lower particle masses, the core is extended enough, and therefore you overshoot the bulge, right? For example, for an extreme solution of below 1 keV, 0.6 keV, the core is so extended that you overshoot. So the solutions below, let's say, 10-ish keV, you start to overshoot the bulge, so are discarded by this model. Interestingly enough, this coincides with another independent so-called Gannon-Tremaine famous bound by the collisionless evolution of the dark matter particles, in which you know the lower bound of the particle masses has to be above the few keV, but this is another similar bound only from galaxy rotation curve fittings in this model. And why in the other regime, why this maximum mass is because above this particle mass, the central core collapses. And I will come later to this point. Yes. Then we can go one step further here, because you may wonder, okay, but these are the average circular velocity of the S stars, which we know are ellipses. And now has been measured by BLT that this S2 star has a precession behavior, and the gravitational redshift as well, as confirmed by the BLT and also the American group. And therefore, we test this dark matter core alternative to the black hole by, this has been recent paper published this year, by analyzing the S2 star orbit precession. Therefore, we have taken from the literature all the publicly available data of the S2 star astrometry, and we compare our, in this plot, for example, 2 different kind of rare models for dark matter. So one of 56 keV particle mass, so above this 48 bound that I showed in the former slide, and another of 58 keV with the black hole scenario. All of the 3 models can explain very nicely the orbit, but importantly, considering that the dark matter paradigm is an Einstein solution, but in presence of matter, not in vacuum. You know, Schwarzschild solution is in vacuum, and therefore the Schwarzschild solution predicts a unique precession. It's the so-called Schwarzschild precession for the S2 orbit. But in presence of matter, you can have, because you have effects also on the surrounding matter or extended mass, you can have a competitive effects. A prograde precession due to the central core, but a retrograde effect due to the extended mass. And therefore, we have demonstrated that for these particle masses, for example, in a range of 56 until 60 about, we can have different trends. This is very interesting because you can have different trends of precession of S2, which in green here is a prograde precession, which is very similar to the black hole, but in red is a retrograde precession. In this, if you can check in the paper here, the details, but it's interesting that we claim that the best position where you can compare these two models of these two paradigms is when S2 star goes to its next apocenter passage in 2026. And because this is the best case when you can distinguish if the precision will be retrograde or prograde, because up to now it has been measured only at the pericenter passage, only compared with Newtonian case in the case of the VLT. So we have to wait to this few years to try to test these models. And let me finish with the last two slides. We have applied this model to other galaxy types, from dwarfs to elliptical to galaxy clusters. And in this plot, I show typical average values of halo scale length of dwarfs with typical masses of 10 to 7 solar masses here. Then from the thin sample, the nearby galaxies, we have obtained these other average values of one halo scale length. And therefore, we have asked to this model to answer for this fixed halo boundary condition and to find the full family of rare solution that can account for this observation. Interestingly, you can see here the core mass in the case of dwarfs. See, the core mass can go from several 10 to 3 up to 10 to 6. So this is naturally giving an explanation for the so-called intermediate mass black holes in terms of dark matter. And for example, you can see in the spirals that the core mass can go from 10 to 6, 10 to 5-ish solar mass, and to 10 to 8, which is a critical mass for gravitational collapse, and therefore also providing alternatives to the central black hole scenario here. And finally, we have demonstrated rigorously in a recent paper that this kind of model not only may provide alternative to the central massive black hole in terms of dark matter, but also provide a supermassive black hole formation mechanism when the quantum core collapses gravitationally. This can be demonstrated by the so-called turning point criterion, which is a criterion which you plot the central density. If you see here, for example, in this typical spiral case, as central density rises, the core size shrinks. And therefore, while central density increases, the core mass increases, but until it reaches a maximum in this curve, interestingly. At the right of this maximum, there are theorems that tells you that solutions are unstable, and therefore should collapse to a black hole. We have demonstrated this, and therefore, for a typical fermion mass of 50 keV, the critical mass for gravitational collapse is about 10 to 8 solar masses, which is an interesting number because it kind of divides the non-active galaxies to the active galaxies. So it may be the case that according to this model, that non-active galaxies may not be black holes at the center, but dense concentrations of dark matter, while active galaxies, they should be dark matter, they should be, sorry, black holes. I finish here, and I'm open for questions. Sorry, let me conclude. So I would like to state the fourth big conclusions of this talk, which is accounting for the quantum dark matter nature in the relaxation of halos can lead to a novel fermionic dark matter profile, which develops a dense and compact core surrounded by a halo. These core halo profiles can explain the galactic rotation curves while provide an alternative to the central black hole in non-active galaxies. And for fermion mass of 50 keV, this dense core can explain the precise astrometric data, all public data of the S stars around Sagittarius A star, including the precession and relativistic ratios of S2. And finally, they can also provide a supermassive black hole formation mechanism from gravitational collapse of these quantum cores. For the listening.
Thank you very much. I'm afraid we don't have time for questions. So we're going to move on to the next talk, but please don't hesitate to approach Carlos during lunch and leave questions for him on the Discord server for the people online.
Thank you.
So we thank Carlos again. Very nice.